Welcome in. All right, so here's a pretty cool example. It's on Hooke's law, and it's with a healthcare kind of a twist a little bit. So we're going to try to solve this. I'll put the references for this in the description below. All right, so we have a physical therapy clinic and an elastic resistance band, which is capable both of stretching and compressing, so it's kind of like a spring, is used to help patients recover from muscle injuries. The band behaves like a spring, and its force constant is crucial for determining the appropriate resistance for each exercise. And that indeed is true. So a patient is undergoing physical therapy, and a resistance band with a known force constant is used in their exercise routine. So here's a set of 5 questions, okay, with these kind of elastic resistance bands. Question number 1. The therapist measures that when a 2.5 kilogram weight is attached to the resistance band, the band stretches by 12 centimeters. And we want to calculate the spring constant, okay, or the force constant of the resistance band. Okay, so, well, let's take a look and jump into this. So this would have been, okay, so number 1. So let's write down the given pieces of information. We have a mass, which stretches this out. It's 2.5 kilograms. And it is attached to the resistance band, which then stretches. So now notice that the stretch is 12 centimeters. So this would have been our displacement. So we can write our displacement. I'll write it as x because it's related to Hooke's law. Okay, so we can certainly write the displacement as delta d, okay, if we wanted to. So it does not really matter as long as we understand that this has to do with the stretch. Now I'm going to keep this all in metric standard units. So I'm going to change that centimeters to meters, and now calculating the spring. So how does this fully out work? So if you have a band, so let's say, so here's your band, and then there's some mass, okay, which stretches this band. All right, so let's say that this is my mass over here, and so this will stretch it out. That mass is equal to 2.5 kilograms. And we know that here, so we have a force of gravity, which is going to be pulling this down, which is going to be mass times gravity, or simply 2.5 times 9.8 meters per second squared. And that would have been our total gravitational, okay, pull due to the mass itself, right? So this is what we would have, and that's what we're going to assume. So now, of course, the spring, okay, is going to try to kind of push this back, and it's going to try to equate this, or at least there's going to be some elastic kind of potential stuck in there, so that you're going to have a spring, which is the restorative force, which tries to push this back. Now, with that mass hanging there, so that means that these two forces are equivalent. So we know that we would have our force of gravity is going to be equal to the spring force, okay, as well, that we would have. Now, that force is going to be upwards. So now what do we know from Hooke's law? Well, so we know that the spring force is just negative k times the displacement. Now the negative just simply means the direction because it's opposite to the displacement within here. Now our direction is upwards, so we already know that, so I don't have to put the negative in here. So this is going to be just k multiplied by the displacement, or the stretch in this case. And then the left-hand side is going to be mass times gravity. So now if you substitute all of this back in, you're going to get 2.5 times 9.8 is equal to, so that is 0.2. I'm going to put that first, and then I'm going to put the k on the other side. So now you can certainly solve for k by simply taking and dividing both sides. So I'm going to duplicate this back in. So this is going to come down right below there. And we have our k. All right. So let's jump this in. So 2.5 times 9.8. And then this is divided by 0.12. So our k is going to be equal to 204.1, 6666, etc. Let's, we can round this to 3 significant figures, although it doesn't state that, but we'll just do it for the sake of this example. And this would have been Newton meters, right, as our constant. And here you go. So that would have been answering part number 1. Here's part number 2. Calculate the displacement of the same resistance band when a 4 kilogram mass is attached. So if you now increase the mass or the weight, well, what will happen? Now we're going to assume that the resistance band applies kind of as an ideal, spring, okay, that we have, or an ideal elastic band. So it's going to carry the exact same constant. So here's our constant that we found. And for number 2, so maybe I'll switch colors, we have a 4 kilogram band. So all that happens, really, so if I now take all of this in here, I'm going to duplicate it, switch the color to make it green. And now instead of 2.5, this is going to be 4 kilograms. So I'm going to just write that in there. And that's exactly the same style of problem. Now, except in this case, we know what the K is. So what we would have is now 4 times 9.8. So this is our force of gravity, okay, that we have. And then on the other side, which is the spring itself, and except now we do know what that constant is. So within here, I'm going to use the unrounded value, and you should typically do that if you're carrying through questions. And now we want to be able to know what that stretch will be. Well, so this would be equal to, and on our calculator, so we would have, 4 times 9.8 divided by 204.1, 666, etc. So we have this as our stretch, and notice it would stretch quite a bit, and 0.192. So again, I'll keep it to 3 significant figures. This is in meters, so this is really 19.2 centimeters if you were converting it back in. So that would have been the stretch that we would have observed for a 4 kilogram mass. So that's number 2. Number 3 states, suppose the 4 kilogram mass is pushed upward, compressing the resistance band by 10 centimeters. So notice that this resistance band can both stretch and compress. It's kind of like a spring. So now by 10 centimeters, what force would be needed to keep things in equilibrium? Include a free body diagram. Okay, so what happens in here? So if we take this exact same thing, so I'm going to take the mass itself, all right, so a free body diagram, I'm going to just draw this out. So there's no change, so force of gravity is still 4 times 9.8. Now, if this is being compressed, okay, so if you're going to be compressing this through, so we have to be careful in here. So if you compress it, then the actual force of the spring is going to be in the opposite direction, right? So that's where the spring will be. So they're both actually pointing downwards, right? So force of gravity is trying to pull this down, and then the actual, I'm using spring, although it's the resistance band, it's going to be in the opposite direction, right? It wants to do, okay, the opposite of the fact that it has been compressed by 10 centimeters, all right? So this is, the compression in there is 10 centimeters or 0.1 meter. That's what we have. Now we're using the exact same spring, so we're going to have the same constant in here. And now if you want to keep this in equilibrium, so obviously if you're compressing this, that means, you must be pushing upwards in some way. So I'm going to put this, F push, all right? So you're pushing this upwards so that it just remains in equilibrium, because you're certainly not going to be pulling it down because those forces are already downwards. So don't forget, so F net is equal to the sum of all of the forces that we have. Well, what are all of the forces? Well, first of all, the net force is 0 because it says it's in equilibrium. Then you would have had the pushing force. So that one is upwards. I'm going to make that positive. And then the other two would be negative. So your force of gravity, which is just mass times g. And then your restorative force from the elastic band. And this would have been K times delta X from Hooke's law. So there you go. So if you take this out, we can certainly substitute all of the values back in, and we can find out and solve for F push. So F push is going to be equal to, so if you kind of switch the sides over so the signs will change, it's going to be 4 times 9.8 plus the constant, which was 204.16, etc., times 0.1. And now when we add these two, we're going to get exactly what that force would be. So there you have it. All right, so this is what we would have. Now again, I'm assuming that it's on the vertical, so I made the direction upwards, but whatever the compression will be, it is in the opposite direction there. All right, so there it is. Okay, so that would have been for number 3. So this is a good one. Now for number 4, it says determine the acceleration of the mass at the position above once released. So, well, in this position right here, what's going to happen, right? What will be the acceleration if we release it? Now, the acceleration will be downwards. So we know that because once we remove our push, right, then the spring and the gravity itself are going to now start to make this accelerate. So therefore, once you remove this, notice then all you have is you're going to have your net force, okay, is going to be equivalent to this, so to that right-hand side. And so from this, so F net is no longer going to be 0. Your F net is going to be 59.616, etc. And that is equal to mass times acceleration, right? Now, the mass is just 4 kilograms. So we can get what the acceleration is by dividing the force by 4 kilograms. So if we do that, divided by 4, this is going to be 14.9 meters per second squared. Okay, so, and it is going to be downwards if you're substituting it back all in. So there you go. Okay, so that is number 4. And that leaves just one more, which is number 5. Let's take a look at that. If a different elastic resistance band was used, where a mass of 5 kilograms stretched the band by 8.5 centimeters, then what amount of elastic energy would be stored for that stretch? Okay, so that's a nice example and a question. Now, this is completely different from the previous example, meaning that I can't use any of the other information in here because the values are different. So we're going to have to do this computation. So first of all, notice it's asking us for elastic energy. Now we're going to assume that it's all ideal. So the elastic potential energy that you have is 1/2 times the constant and then your displacement squared. Okay, so this is where that elastic energy, so you can remember that formula. I can put up a link up above there if you like, okay, if you want to see the introduction to this and how to derive that. Now, if you substitute all of the values in here, we have this. So that's great. This is 0.085. However, we don't have K. So we have to find out what K will be. So this is kind of a two-step process. Now we can find out K from the viewpoint that we know what the mass is doing. So it's stretching out the band and it's by 8.5 centimeters. So we can do the exact same thing we did in question number 1. So meaning if we had our band and then, so this is going to be mass times gravity, except it's 5 times 9.8 within here. So that's going to be, I guess, 49 newtons. And then, so this will stretch this out, so the band, by 8.5 centimeters. So that is the actual stretch, which means that we can now equate both of them. So the force of gravity is going to be equivalent to the spring or the resistance band, and that's going to be K times delta X. So now substituting, so this is 49 newtons. This is 0.085. So now dividing the left-hand side, we can find out exactly what that would be. So 49 divided by 0.085. And this one is 576.47, etc. And this would have been Newton meters. So now substituting it back above there for the energy itself, so elastic energy, elastic potential energy, that's what the P is, just potential. So I'm going to take 1/2, substitute this K in here, so that's 576, etc. And then 0.085, and that's going to be squared. So since I have this already on my calculator, and I'm going to multiply this by 0.085, this is squared, and then I need that half. And there is, okay, so let's round it to 3 sig figs. And so this is not a lot of energy, right? So it's about 2 joules of energy. So that's the question, okay, the last one, and how you would solve it. All right, so I hope that you found all of these examples useful, and it gives you a hint on how to solve Hooke's law, relating it back to a nice little short healthcare example. Thanks for watching. Okay, we'll see you in a future video. Bye, everybody.